Hello and welcome to the Daily Space for Tuesday. It's not Tuesday, for Thursday, May 24th, 2018. I am your host, Dr. Pamela Gay, and I have to admit I know where I am, but I struggle a bit with when I am. As always, we're going to bring you a roundup of today's news in astronomy and space science. This is a daily show, Monday through Friday, same day, same time. Please, if you like what you see, spread the word and let's get more people learning about this universe we share. Now, I want to start out by reminding you that our own Earth is indeed a planet. So here, and I have camera issues. Sorry, it turns out I had help with my camera at some point. So it turns out our own Earth is a planet, go figure. And it occasionally acts out. One of the biggest things that has been in the news with our own planet recently has been the eruption of Kilauea volcano down in Hawaii. Now, this is a picture of its caldera, and this isn't actually where the lava is coming out. Instead, with this shield volcano, we see remarkable flows of lava that are pretty much just randomly rising up out of the earth. Here is a satellite photo showing a variety of these different fissures that have opened up. We are now up to 22 fissures that have emerged, and the lava is now racing towards the ocean. When we think about this volcano, the way it's getting talked about in the news, the way it's getting talked about on Twitter, you may think that massive swaths of Hawaii are being affected, but the reality is that if I zoom out a bit, this red flag, and I'll make this a bit bigger, while this is a very difficult situation for the people living in the subdivision, Hawaii as a whole isn't particularly affected. In fact, if I zoom out even further, the red flag continues to mark the place of the caldera of Kilauea. Off here to the west, pretty much under the letter A in Pahoa, this is where the volcano is making itself felt. And Mauna Kea Observatory up here in the northwest of the island is experiencing much less trouble. Now, all because it's not having any trouble doesn't mean it doesn't see the volcano. In fact, this is a single snapshot taken from Gemini Observatory, pointed out over the cloud cover toward the Kilauea volcano and these fissures that are erupting. The glow that you see coming through the clouds is actually from the lava beneath. In this time series of photos that were taken throughout the night, you can see the stars moving through the sky, and you can start to resolve more and more of where the effects of the volcano are taking place. Now, this isn't the same kind of volcano that we are used to hearing about in Indonesia or the Philippines or anywhere along the Ring of Fire. This isn't a volcano that is caused by either the plate tectonics having one plate go under another, or like with Iceland where the plates are diverging. Rather, this is a hot spot in our own planet's crust, where for reasons that aren't entirely clear, we have a plume rising up from deep in the core of the Earth, and as it rises up, it melts the outer crust of the planet and ends up creating this trail of volcanoes as the plate moves over the top of this stationary mantle plume. In the case of Hawaii, we actually see this train of islands moving out across activity, it makes us sit up a little bit and start thinking what other hotspot volcanoes are out there. And the one that gets talked about the most is the Yellowstone caldera. Yellowstone National Park in northern United States, in the northwest United States, is, well, it's what's called a supervolcano. When this goes, it's going to affect massive portions of the United States and Canada directly, and indirectly through putting ash into the atmosphere and cooling the temperature of our Earth a bit. It's going to affect the entire planet. This particular hotspot volcano has gone off as recently as 640,000 years ago. And through studying the layers of rock in this region of the United States, this region that cuts across multiple states, we're able to trace out eruptions from 640,000 years ago, 1.3 million years ago, 2.1 million years ago. And as we study all of these, and as we directly measure the rising dome of this volcano that is tilting a nearby lake, we have to question, when will this volcano go off? And the answer is, we don't know. We don't know. Oh, I'm being told that full screen mutes. I will not go to full screen again. I'm so sorry. Okay. I will not go to full screen anymore until I get that fixed. So what I said on the prior slide is here with the volcanoes. You can see that the the westernmost volcanoes are flattened out to the point that they are now down below the surface of the ocean. And as we move through the Hawaiian island chain, we get to see things finally that are starting to rise up out of the ocean. Here's Honolulu right here. And as we move toward the east, and in fact, as we get to the easternmost edge of Hawaii's Big Island, we're finally able to encounter the active volcanism. Now, with this particular chain of hotspot volcanoes, it makes us question what other hotspots are out there. And this is what brings us to Yellowstone. Now, we can't know when Yellowstone is going to erupt, but for now we can enjoy things like the grand prismatic springs shown here on the right, the hot geysers, the hot springs, all of the amazing features that are found nowhere else in the world that are associated with having, well, magma so close to the surface of our planet. So stay tuned. It could be tomorrow. Probably not. We haven't had enough earthquake activity for that to probably be the case. But maybe in the coming years, the coming centuries, or the coming millennia. We don't know. This volcano will once again, cover large parts of the world in ash and cover a small but meaningful part of the planet with lava. Now, looking at other planetary surfaces, I have a quick update on a story from last week. I mentioned last week that NASA scientists were working to try and figure out how to get the broken drill on the Mars Curiosity rover, well, drilling again. The problem that they'd run into is the drill normally extends out a set of probes that it rests against a rock. And while it's stabilizing itself with these probes against the rock, the drill comes out and drills. Well, that wasn't working anymore. So what they're doing instead is they're extending the drill bit past those probes and using the arm itself to push into the surface of the rock they're trying to drill into. This particular hole is about 2 inches deep, and it was drilled on May 20th. It's only about zero point 0.6 inches across, but this is enough for us to start to see what is, well, this particular rock like just a little bit beneath the surface. This is a fabulous breakthrough. The Mars Curiosity rover hasn't been able to drill any of these boreholes since December 2016. This means we haven't been able to get a better, deeper, literally through the rock, understanding of the geology of these rocks. So now we're back to being able to drill. Now, moving a little bit further out through our solar system, trying to understand Pluto has been, well, a topic of much discussion since the New Horizons mission sent us back images of this amazingly complex, in ways we never anticipated, surface. It was predicted that Mars would be completely covered in craters, a battered, icy world. But what we see instead is this large plain of almost no craters at all. This is Sputum Planum. It is the heart that you see in full planet images of Pluto. And it is a nitrogen sea, a frozen nitrogen sea. Trying to understand this, scientists working at the Southwest Research Institute have worked on models to construct Pluto in two different ways. In one model, they imagined it to be built up out of amalgamation of billions of comets from the Kuiper Belt. So imagine comet after comet after comet colliding, sticking together, gravitationally pulling in other future comets, and through this small objects building up into a larger object process was able to create Pluto. Now, they used to build their model the chemical composition of comet 67P, which was explored by Rosetta last year. It turns out you can mostly explain Pluto as being built up out of this myriad of comets, but you can't completely explain it this way. One of the problems in doing it is there's a lower abundance of carbon monoxide on Pluto than would be expected if it was just basically a large snowball made out of smaller snowballs. To try and understand this low abundance of carbon monoxide, scientists, well, they first tried modeling to see, could you have built Pluto up directly out of the solar nebula? The problem they ran into with this model is the chemical composition just didn't quite match. The next thing they imagined is what chemical reactions would take place if you had a subsurface ocean. It turns out that if you have a burial of subsurface ices, they could be destroyed in the presence of liquid water. So this is yet one more piece of evidence that maybe Pluto has liquid water under its surface. Now, I have one out of this world, or out of all of these worlds, story to bring you, and this will be our last story of the day. Scientists recently discovered a very odd supernova remnant outside of our Milky Way galaxy. This particular supernova remnant, with the complex license plate name 1E0102.2-7219, this object is located in the Small Magellanic Cloud, about 200,000 light years away from Earth. Scientists studying this particular object using the Hubble Space Telescope and the Chandra X-ray Observatory were able to sleuth out the exact location of the neutron star that's in this supernova remnant. If you look at this picture, you'll see in the bottom center of that blue ring that there's this little red circle. Inside that little red circle is where the neutron star is located. Now, this raises the question, how is it that the neutron star, the thing that was the origin of the supernova explosion, how is it that it's so incredibly off-center? Well, there's two basic possibilities. One is that the neutron star is moving at a high velocity due to an asymmetric supernova explosion, an explosion that went off more on one side than the other and gave the star a kick of 1,000,000 miles per hour. Now, the problem with that theory is that red ring around the neutron star, how is it still around the neutron star if the neutron star is moving? Now, another idea, one that I think is more realistic, is that that ring of blue gas that we're seeing was given off by the star that went supernova far in its past. That what we're seeing is material that was given off through solar winds, through loss of the star's outer atmosphere, and then was shocked by the supernova into this bright glow. And that inner red ring, that actually was formed during the supernova. So that star was moving very slowly, drifted away from the atmospheric bits that it had given off, and then went supernova. So this might be a very complex kinematic tale. This is one of the few supernova remnants that we've discovered that has this neutron star down in its core and doesn't show any signs of there being a stellar companion. This indicates that this was a massive star that lived out its life, and when it stopped generating light in its core, collapsed down so violently that it created a supernova. And the core that was left behind was so massive that the only thing it could do was collapse down into this neutron star. So whatever the future this is, we'll bring it to you when we know more, when we have more observations and more understanding someday in the future. For now, though, that brings an end to today's episode of The Daily Space. This is a production of CosmoQuest. We are part of the Astronomical Society of the Pacific, a 501c3 nonprofit dedicated to putting science in your brains. Do you want to do more, learn more, get engaged? Join us at CosmoQuest.org, where we invite you to help us map out other worlds in our solar system and increase the maps we have of our own planet Earth. So, if you like this show, give us a follow. Follows are free. If you want to see us keep producing this show into the future, please help sustain our efforts with a subscription. And remember, every little bit helps. So once again, this has been The Daily Space. Now, I'm here and I will take your questions over in the chat. Please, if you could go ahead and @ me, it will make it easier for me to find your questions in the thread. I would like to apologize once again for failing to get all of my audio set up 100% correctly. Thank you so much, everyone, for pointing that out for me. So, do we have any questions today from anyone out there? I'm going to go ahead and try and recenter my camera a little bit. We're still trying to figure out where best to put the camera so that moving around the monitors doesn't also move around the cameras. So I see Azuriel is asking, the Curiosity rover's new method of drilling, wouldn't it put pressure on parts of the rover that shouldn't be taking pressure? Well, it does indeed increase some of the wear and tear on the arm of the rover. But it was decided this was a safe enough thing to do to go ahead and proceed, that any possible risk, thank you so much, Scott, for the subscription, that any possible risk would be outweighed by the science potential. And yeah, it is probably a bit awkward, but isn't drilling always awkward? So I see Hanny is asking, would LIGO have been able to hear the asymmetrical neutron star go off? No. LIGO, what it generally hears, what it's able to detect are gravitational waves moving through our universe that are generated through the merger of neutron stars. So one neutron star getting formed in a supernova isn't the kind of event it's able to detect. What it's able to see instead is if you have two neutron stars going around each other that coalesce, or two black holes going around each other that coalesce. It's that key of having two different objects that creates the gravitational waves and gravitational radiation that LIGO is sensitive to. So Israel is asking, what is the black sand made up of in the same picture you showed of the drilling? So let me go ahead and pull this up. Um, I don't know. Um, Mars is made of many different chemicals. It has hematite, it has iron-rich dirt. That's why there's so much rust. I don't know in particular what this dark color is. Um, as a wild guess, and that's what this is a wild guess, I'd guess that it is something similar to hematite, which is a dark mineral that forms in water, but that is totally a guess. Um, okay, going back to finding where the chat just disappeared to. I lost my chat. Too many windows. Pardon me while I become confused for a moment. There it is. Guido is pointing out that there was a good question at the beginning. I'm sorry I missed it, about what happens when the lava hits the ocean. So let's go ahead and pull up that map we had earlier. Big J, Eddie can go ahead and come back in. That's fine. So here you can see that the lava is beginning to hit the ocean, and the chemicals in the lava mixing with the water actually release toxic gases. This is called blaze, which is lava vapors essentially. All sorts of nasty carbon-rich molecules, sulfide-rich molecules, can come out of this. Don't go near the place in the ocean where the lava is interacting. The kind of lava that's coming out of Kilauea is actually, for the most part, slow moving. It's the kind of lava that if you want to get close to lava, this is the lava to get close to, but only do this if you're a trained scientist who knows what you're doing. That's fine when you're inland and you have sensors for the gas. All of these vents can be releasing toxic gases. With the ocean, it's particularly bad because of all the chemical interactions and the steam that comes and carries those toxic gases. So do not approach. Do not approach. Let's see, do we have... so Sicaria 1 is, how come there is no physical barrier between our atmosphere and the vacuum of space? Gravity is what keeps us safe. So let me go back to just me. So our planet, I'm looking to see if I have anything round on my desk. I don't. So our planet is a ball of rock, essentially. And the gravitational pull of our Earth's mass on our atmosphere is greatest near the surface, which is why we have the greatest atmospheric pressure down at the surface of our planet. As you go higher and higher and higher up, the effects of gravity lessen. And with the lowered effects of gravity, the atmosphere can get thinner and get thinner. And eventually, about 65 miles up, you hit this point that we call outer space. At this point, there isn't sufficient squishing, well, there just isn't sufficient atmosphere. Atmosphere has started to be able to drift away. There simply isn't enough atmosphere to still be there at that height. Gravity is less. So up at that 65-mile mark, we start to call that outer space. The International Space Station orbits at about 300 miles up, and it does still encounter small amounts of drag from the atmosphere. This small amount of drag is enough to force us to have to continually boost the International Space Station before it gets dragged down into a lower orbit. But overall, the picture we have is this gradual gravity holds things to the surface, gravity holds things to the surface. And as the gravity gets lessened, and as we just run out of Earth's gravity, the atmosphere gets lessened. And we start to call it outer space. when when the atmosphere gets to that thin diffuseness that it has at 65 miles up. Now, another way to think about this is if I put a drop of water on the surface of my table, you'll get a dome of water. In this case, what's holding that dome in place instead of getting sucked into the atmosphere is the surface tension of the water. Now, that's different physics, but again, you have chemicals that are being held together. Our atmosphere is held in place by gravity. Surface tension holds that drop of water together. And both of them can be harmed. If we didn't have our Earth's magnetic field, solar wind would push our atmosphere away, but the magnetic field protects us. Basically, it's physics. There's a slow, continual graduation from the surface to outer space. And we're very glad for that magnetic field, because while our atmosphere would have gravitationally been held onto for a while, it probably wouldn't have been long enough to allow us to be going out and enjoying, well, here I have great weather today. So let's see, what other questions do we have here? So Hanny is asking, how are continents formed? Well, I'm going to pause on this one for a moment. The reason I'm pausing is our Earth has had layers of lithosphere floating on top of its hotter internal bits, and then there's the crust and everything, as far back as we've been cool enough to have a solid surface. And the continents are formed by these plates of crust moving around on the surface. So the continents are a manifestation of where the Earth's different plates are located at any given moment in time. And these plates are constantly on the move. Now, part of the way the plates are constantly moving is when they collide, such as what's happening where the Himalayas are right now, they buckle up and form mountain ranges. Where the plates go underneath one another, old crustal material will get completely destroyed, remelted into the internal bits of the Earth, remelted into the mantle. Where plates are pulling apart, new material is recycled to come up to the surface. So the material of the plates is constantly being recycled. This is why I can't point to any one place on the surface of our planet and say this place is 5 billion years old, even though that's roughly how old our planet is. I can't even say this piece is roughly 3 billion years old and has existed since the moon was formed. We have to basically say continents are just how we draw our geopolitical boundaries. It's how we look at this set of plates are bound together at this moment in time. And the crust that makes up those continents is constantly on the move and constantly forming and reforming new continents over the millennia. So Itchy is saying, do the colors in the image of the nebula, and let me go ahead and pull that image up. Do the colors in the image of the nebula surrounding the neutron star you spoke of correlate to specific elements? Yes. So I'm trying to remember all the different elements that are in here. I believe the green is corresponding to oxygen, and I don't know specifically what all the blue and red are responding to. I know that those are Hubble images. Let me see if I can look that up for you real fast. It looks like I don't have that screen up at this point. If you go to the Chandra website and I'm still looking to see if I can find it here. It should be up on the Chandra site. Let me back up a moment and look for it. Here we go. So chandra.si.edu is where this is located. So the green is oxygen. The red, it's simply saying is gas, and let's see if it tells me what the blue is. So the blue and purple are from the Chandra X-ray Observer. The red is from Hubble Space Telescope. It's not telling me what these are specifically. All I can tell you is the green is oxygen. So Peter, we can't ever predict accurately when which volcano will go off. That particular one, I believe that's the one near Naples. Let me double check. And it is a fairly angry volcano, but let me look. So this is this is the volcano that's near Naples. I don't believe this is a shield volcano, though. I'm double checking. So there's a lot of volcanism around Italy, and I'm not seeing instantly what kind of volcano this is. It is another supervolcano. So I would have to look up more about this to answer your question. I am going to see if I can figure out if it's a hot spot or a different kind of volcano. There was a lot of excitement back in 2017 trying to understand it. There was a set of Italian scientists that, for reasons I can't explain, thought it would be smart to drill boreholes into the magma. It didn't go off. Yeah, I'm not seeing quickly what kind of a volcano this is. So I'll have to do more research on that. You're allowed to know more than me about things, Peter. I don't know everything. So I just don't know that much about that particular volcano other than it's a supervolcano near Naples that occasionally breaks bridges in Naples because of how it's tilting the surface of the planet. Okay. So, Faring H, we don't know how rapidly this kind of a way of forming Pluto could have occurred, so I can't answer if Pluto would be younger than the inner planets. Hanny is saying, could a planet without plate tectonics maintain life? We don't know. So I think a better question is without tectonics. Our Earth, with its moving plates on the surface, seems to be fairly unique. Venus has had massive upwelling and outbreaks of volcanism across much of its surface in its past, if we're interpreting Magellan radar data correctly. Mars doesn't have specific plates like we do, but instead has undergone periods of volcanism. And what is required for life is heat, nutrients, and a solvent like water or methane that allows the chemical processes to take place. It looks like it's possible for places like Europa or Enceladus to support life in deep oceans beneath the ice. Now, the ice moves, it has cracks, it gets restructured, there's ice volcanoes, but it doesn't have specific plates the way our planet Earth does. So heat that will cause the surface to change seems to be necessary, but not plates like we have here on our planet Earth. So Peter, yep, will survive Betelgeuse, Hanny. Destruction is one of my fortes, but I don't keep all details in my head all the time, Peter. So do we have any other questions for today? If not, today's episode ran long, but that's okay because no one is currently waiting for the channel. So thank you everyone for joining me. Once again, this has been the Daily Space, a production of CosmoQuest. We are part of the Astronomical Society of the Pacific, a 501c3 nonprofit. If you like what you see, give us a follow, find out about all our different shows. We will be back tomorrow, same time, same channel, bringing you all that's new in astronomy and space science. If you'd like to help us keep doing this, please feel free to sustain us in any way. We're not picky. So thank you. Thank you for coming. And please consider going to cosmoquest.org and doing some science. We could use your help mapping out other worlds, including our own planet Earth. Now, that's all I've got for today. So wherever you are in the world, have a fabulous morning, evening, afternoon, and remember, go out, look up. Bye-bye now.